walk you through this mean value theorem worksheet. Up here we've got the definition of the mean value theorem. Remember, the function has to be continuous, closed, and differentiable in order for the mean value theorem to be applied. And we're going to go ahead and start looking at number 1 here. Let me zoom in on that. So we know that the function f of x equals 2x squared plus 1 is a parabola, and parabolas are continuous. I'm going to say check continuous, so that works out. Is it closed? Yes, we've got closed brackets there, so we can say check closed. And parabolas, they're nice smooth curves, so smooth curves are also differentiable. So now that we know our 3 conditions are true, we can go ahead and use our formula. So first we're going to find the average rate of change, which this is my A, this is my B. So it's f of B minus f of A all over B minus A. So we can plug in our points. We've got f of 2 minus f of 0 all over 2 minus 0. So to evaluate f of 2, we're going to plug in 2 here. 2 squared is 4 times 2 is 8. 8 plus 1 is 9. Plug in 0, you get 0 plus 1 is 1 all over 2. So 9 minus 1 is 8 divided by 2 will be 4. So our average rate of change would be 4. Then we have to go ahead and figure out what f prime of c is. Well, I have a function f of x, so I need to figure out what f prime of x is. So we derive. Take the derivative of this. The derivative of 2x squared is 4x. We want f prime of c, so all we do is replace the x's with c's. F prime of c equals 4c. And often we'll think of this as the instantaneous rate of change. So we know that our average rate of change equals our instantaneous rate of change, which means in this case, this number has to equal this term. So 4 equals 4c. So c equals 1. So if I were to sketch it, you don't have to, but if I were to sketch it, we've got a parabola that gets shifted up 1, something like that. And on the interval from 0 to 2, right here, we'd have a secant line going from 0 to 2. So what we just figured out was that at c equals 1, when we're at 1, that's the location of our tangent line that is parallel to our secant line. All right, let's check out number 2. So let's see, again, we've got a polynomial equation here, which polynomial functions like that are continuous. So I've considered that it's continuous. It's a closed interval. And again, like the parabola, a cubic function like this will be differentiable. It's all smooth curves. So we can go ahead and use our formula. This is my A, this is my B, f of 2 minus f of 1 all over 2 minus 1. Plug in 2. When you plug in 2, you get 10. When you plug in 1, you get 2 all over 1. So we have 8. Now we go ahead and we take the derivative of this. So we've got f prime of x equals 3x squared plus 1. We're looking for f prime of c, so let's go ahead and plug in our c. 3c squared plus 1. We know, according to our formula, that our functions need to be equal, or our 2 sides need to be equal, so this side needs to equal this side. So 8 equals 3c squared plus 1. Subtract 1, we get 7 equals 3c squared. Divide by 3, 7/3 equals c squared. Take the square root of both sides, and when we do that, we get c equals plus or minus the square root of 7/3. So I think that would be our answer, but it's actually not because of our interval. There's 2 positive square root of 7/3 and negative square root of 7/3, but there's only one of those values is on that interval. So it's going to be the positive one is on here because negative square roots of 7/3 is not on that interval. So my final answer is just c equals the positive square roots of 7/3. All right, number 3. So again, we've got a polynomial function here, which is continuous. Check. So we've considered that it's continuous. It's on a closed interval, and it is differentiable. So we've considered all three of those things. So we can go ahead and proceed to our formula f of 2 minus f of negative 1. Remember, that's your a, that's your b, all over 2 minus negative 1. So we plug in here, 2 to here, so 2 to the 4th is 16, plus 2 is 18. Minus, plug in negative 1 to the 4th becomes a positive 1, plus 2 is 3, all over 3. So that becomes 15 over 3, which is 5. And then we're going to go ahead and derive f prime of x equals 4x cubed. Plug in my c, f prime of c equals 4c cubed. So this has to equal 5, so 5 equals 4c cubed. Divide by 4, so I'm going to flip it around a little bit, right? C cubed equals 5/4. We need to get the c by itself, so we're going to take the cube root of both sides. And there we have it. C equals the cube root of 5/4. Let's move on to number 4. All right, check that it is continuous. Okay, let's talk about this for a second here. This is square root function. So square root function looks something like that. So this function is not continuous on the interval negative infinity to infinity, since it starts right here at the origin. However, on the interval from 1 to 4, it is a continuous function. So it is continuous, it's a closed interval, and then it is also differentiable because from 1 to 4 there's no corners, cusps, vertical tangents, or discontinuities. So let's go ahead and find our average rate of change, f of 4 minus f of 1 all over 4 minus 1. Plug in 4, the square root of 4 is 2. Plug in 1, the square root of 1 is 1 all over 3. So we get 1/3. Now when we derive that, I'm going to rewrite it first. F of x equals x to the 1/2 power. Notice I didn't write f prime of x. I haven't derived yet, I just rewrote it. Now I'm going to derive f prime of x equals, bring that down 1/2 x to the subtract 1 negative 1/2. And I think I'll rewrite that a little bit too. Well, I'll do the c and rewrite it at the same time. So f prime of c equals 1 over 2 square roots of c. So I brought that x to the 1/2 to the bottom, made it x to the positive 1/2. And that's the same as square root. So now we know that this must equal that. So we've got 1 over 3 equals 1 over 2 square roots of c. Now you could cross multiply that if you want, or you can just think when the numerators are equal, then the denominators have to be equal. So we know that 3 has to equal 2 square roots of c. Divide both sides by a 2. So I'm going to get c equal, square root of c equals 3/2. Square both sides. So c equals 9/4. And it's a good idea to check, is 9/4 on the interval? 9/4, 4 goes into 9 2 1/4 times, so it is on that interval. All right, number 5. So check that this is continuous. Ooh, I have a problem here. If I sketch out what this graph looks like, I know that there's a vertical asymptote at x equals -1 because x cannot be -1. It will be 1 over 0, and if 0 is under the line, it's undefined. So at -1, we have a vertical asymptote. And I know that this is a rational function, so I kind of know what rational functions look like, but if you weren't sure, you could plug in a point. Like if you plug in 0, you get 1. So I know that my curve of my rational function is going to look something like this. And then if I plugged in a point over here like -2, I would get -1. So it's going to go something like that. So this function is not continuous. So do you think, oh, I can't use the mean value theorem? Well, where is it not continuous? It's not continuous at -1. And -1 is not on my interval. So on the interval they give me from 0 to 2, this piece right here is continuous. So you have to consider it, but the interval that we're given, it is continuous. Okay, so we've checked that it's continuous. It's closed because of the closed brackets. And differentiable, when you know what the rational function kind of curve looks like, it's smooth from 0 to 2. So check that it's differentiable. And now we're going to go ahead and find the average rate of change. F of 2 minus f of 0 all over 2 minus 0. So we plug in my 2 and I get 1/3. Then I'm going to plug in my 0 and get 1 all over 2. I'll make a common denominator here and get 1/3 minus 2 3/3 is negative 2/3 over 2. You can go about that a couple different ways. Maybe you'll multiply top and bottom by 3, so you'll get negative 2/6, which cleans up to be negative 1/3. And now we're going to derive. Deriving this one, I'm going to kind of do what I did in the last problem and rewrite it a little bit. Since this is a constant on top, I'm going to move this whole term here up to the top and make it negative. So that's going to become x plus 1 to the negative 1. Then I'm going to go ahead and derive that. F prime of x equals the negative comes down. X plus 1 subtract 1, so it's negative 2. And I should consider the chain rule times the derivative of the inside, but the derivative of the inside in this case is just 1. So now when I plug in my c, I get negative 1 over c plus 1 squared, if I bring this whole piece to the bottom. And so now this one has to equal this one, so negative 1/3 has to equal negative 1 over c plus 1 squared. Again, if the numerators are equal, then the denominators are equal. So we've got 3 equals c plus 1 squared. Take the square root of each side, so we've got c plus 1 equals plus or minus the square root of 3. Subtract the 1 over. I'm running out of room here. So I've got c equals negative 1 plus or minus the square root of 3. But negative 1 minus 3, it's going to be a negative value. That's not going to be on the interval from 0 to 2. So the only, oh, my lights just went off. Yeah. So the only one that's going to work or be on that interval is the negative 1 plus the square root of 3. All right, now let's look at number 6. Here we've got cosine curve. Now you might remember from pre-calc, cosine curve starts up at 1 and it makes a nice smooth curve like that. Ends at 2 pi. So we actually, if it completes one period at 2 pi, we're really actually only looking at the first piece of it up over here. So we're really just looking at up here. And so it doesn't matter if it's just that piece because we know cosine curves are continuous, so we can check that it's continuous and check that it's closed. And again, they're nice smooth curves, so it's differentiable. So let's go ahead and do our average rate of change, f of pi over 2 minus f of 0 all over pi over 2 minus 0. F of pi, cosine of pi over 2, we'll think about your unit circle. Pi over 2, we have a coordinate 0, 1, so cosine is 0. And then cosine of 0, when you plug in 0 here, cosine of 0 is right there at 1, 0, so that's 1 all over pi over 2. You can multiply top and bottom by 2, so you're going to end up with negative 2 over pi. Well, that's your average rate of change. Now we're going to derive f prime of x. The derivative of cosine is negative sine of x. Plug in our c, f prime of c equals negative sine of c. So this piece should equal that piece. So negative 2 over pi equals negative sine of c. Oh, I don't like having a negative on both sides, so I'm going to go ahead and divide by a negative and make them both positives. So now I've got the sine of c, I'm going to flip it around, equals 2 over pi. So we need to get the c by itself. We need to separate it from that sine. So the only way we can do that is we are going to sine inverse both sides of the equation so that those cross off. So I get c equals the sine inverse of 2 over pi. All right, let's go ahead and look at number 7. We've got that situation again where we've got a rational function here, and because we know the denominator can't be 0, it's not continuous at 0, but once again, 0 is not on my interval, so then we're okay. So it is continuous as long as the interval didn't include 0, which it doesn't. It's closed, and again, it's a rational function. It's going to be differentiable, except at x equals 0. So we can go ahead and do f of 2 minus f of 1/2 all over 2 minus 1/2. Plug in my 2 and I get 3/2. Plug in 1/2, I'm going to get 1/2 plus 1 would be 3/2. So I'm going to write this out. 3/2 over 1/2. All over 2 minus 1/2 would be 4/2 minus 1/2 would be 3/2. Don't even think about crossing those two off because this is all part of one big group up here. So let's clean it up. So we've got 3/2 minus, can multiply top and bottom here by 2 and get 3 all over 3/2. Then I don't like having fractions. This is a complex fraction. So let's multiply the whole top by 2 and the whole bottom by 2, which will give me 3 minus 6 all over 3, or negative 3 over 3, which is negative 1. So now let's go ahead and derive it. Ooh, to derive this, I'm going to rewrite it. You could do the quotient rule. Hi, D-low, my slow D, hi. But I'm gonna go ahead and divide it because I can separate it into 2 parts. You can have x over x plus 1 over x. If you split it, because there's just a single term in the denominator. And then that cleans up nicely. Notice I'm not writing prime here. I haven't derived yet. This is just x over x is 1. I'm going to write this as x to the negative 1. Now that's pretty nice to derive. F prime of x equals negative x to the negative 2. Plug in my c. F prime of c equals negative 1 over c squared. So set this equal to this. So we're going to get negative 1 over c squared equals negative 1. You can multiply both sides by a negative, so they both become positive. So really, again, if you wanted to cross multiply or multiply both sides by c squared, you'll end up with c squared equals 1. So when you square root that, you're going to get c equals plus or minus 1. But again, negative is not on that interval, and the negative 1 isn't, so my only answer would be c equals 1. All right, next. Number 8. Sine curve. The sine curve, if you know what cosine curve is, looks like, hopefully you remember the sine curve starts at the origin and goes something like that. So it is continuous. Check continuous. Again, it's closed. Smooth curve, so it's differentiable. And we're going to do my average rate of change, f of pi minus f of 0 all over pi minus 0. So we've got the sine of pi minus the sine of 0 all over pi. And think about where pi is on our circle right there. So it's negative 1, 0. So my sine value is 0 minus, oh, interesting. So minus sine of 0 is 1, 0. So sine of 0 is also 0 over pi. So 0 divided by pi is 0. So now we need to derive f prime of x. is cosine of x. We can plug in our c, f prime of c equals cosine of c. So this piece needs to equal that piece. I'm going to get 0 equals cosine of c. Similar to number 6, we need to get the c by itself. So you could cosine inverse each side, and that would work, but then you have to think about what the cosine inverse of 0 is. Or you could just think, what is cosine of what is 0? So cosine, when is cosine going to equal 0 on your unit circle? So cosine equals 0 up here and down here. So I could say that's true when c equals pi over 2 and 3 pi over 2. But 3 pi over 2 is not on that interval, so my only answer is going to be c equals pi over 2. Let me talk real quick about why this one worked nicely like that and number 6 didn't. So 0 is on our unit circle for cosine. When we go back and look at number 6, 2 over pi, there's no pretty angle on our unit circle where the sine of that angle is equal to 2 over pi. Maybe if it was like the square root of 2 over 2, or 1/2, or just 1, or 0, then we can find nice angles where that works out on our circle. But in this case, because 2 over pi isn't one of those special numbers we know from our unit circle, that's why we had to do the sine inverse and just leave it like that. I mean, you could punch that in and get a decimal answer if you wanted to. But number 8 worked out because in number 8, 0 is on our circle. All right, and our last one on this side, lucky number 9. So we are going to, let's think about what the graph of this one looks like. This one is a radical square root function here. Might help me to graph it if I rewrote it as negative x plus 2. And then I'm even going to rewrite it a little bit more. This is should hopefully take you back to your pre-calc property days, or even algebra 2 property days, where if I pull out a negative, then that becomes x minus 2. So I know it makes kind of a shooting arrow like the square root thing in number 4, but when it's x minus 2 on the inside of parentheses here, it gets shifted either left or right. And I always think when it's a parentheses, you do the opposite. You go the opposite of what you'd expect. So if it's negative, you actually go to the right. And then normally, if that negative wasn't there, I just make it go shooting out this way. But when there's a negative on the inside, it reflects on the y-axis. So it actually causes it to shoot out this way. And if you didn't know that, you could always plot points, make an XY table, and plug in numbers, and you start to see points that go out that way. But a function like this, that is continuous. On -7 to 2, we have to be careful, because if it said -7 to 3, we're out here, nope, wouldn't be continuous, because it stops at 2. It is closed, and it's differentiable. It's a smooth curve, no corners, cuts, vertical tangents, or discontinuities. All right, so let's go ahead and do our average rate of change. F of 2 minus f of -7 all over 2 minus -7. F of 2 is 0 minus f of -7 would be 2 minus a -7 would be 2 plus 7 is 9. The square root of 9 is 3. Oh, how nice they are to us. And then 2 plus 7 is 9, so that cleans up to be -1/3. And I'm going to rewrite this so I can derive it nicely. I'm going to write that as 2 minus x to the positive 1/2. So we've got f prime of x equals 1/2 times 2 minus x to the -1/2. Because we subtracted 1, but don't forget the chain rule, times the root of the inside, so it's times -1. So then that becomes f prime. I'm going to rewrite it and plug in my c in the same step. So I've got a -1 in the numerator over 2, and then I can bring this whole thing down to the bottom and make it a positive square root of 2 minus x. Oh, not x, be c, 2 minus c. And then this piece here should equal this piece over here. So we've got negative 1/3 equals negative 1 over 2 square roots of 2 minus c. If the numerators are equal, then the denominators are equal. So I can say 3 equals 2 times the square root of 2 minus c. This is I gotta start writing small here. I'm gonna go ahead and, should I square both sides now or divide the 2? I think I'll divide the 2. So if I divide both sides by 2, those cancel. And then I'll go ahead and square both sides. So I've got 9/4 equals 2 minus c. So I'm going to subtract the 2 to the other side, which would be 9/4 minus 2. But instead of writing 2, I'm going to write 8/4 equals negative c. Since 8/4 is the same as 2. 9/4 minus 8/4 is negative 1/4. No, it's positive 1/4 equals negative c. And then divide both sides by a negative, and you get c equals 1/4. C equals negative 1/4. Yeah, there you go. Which is on that interval. Let me say that again. 9/4 minus 8/4 is 1/4, but it equals negative c. So you divide by a negative, and you get positive c equals negative 1/4. All right, that's it for this side, and we're going to flip it over in just a moment. All right, now we're going to look at Rolle's theorem. Rolle's theorem is just a specific case of the mean value theorem. In Rolle's theorem, like the mean value theorem, the function needs to be continuous, closed, and differentiable. So you always need to check those 3 things first before proceeding. But Rolle's theorem, unlike the mean value theorem, has this little bit of information where it says, if f of a equals f of b, then there exists at least one number c between a and b such that f prime of c equals 0. So Rolle's theorem, like a Rolle, is all about the number 0. So let's look at number 10 here. Number 10, we've got an absolute value function. So let's consider what that graph would look like. Now, absolute value functions make v's, and it's inside the absolute value here, so it's going to go the opposite of what I'd expect. So it's going to go to the right too and make a v. Again, if you're not comfortable with knowing how to graph functions like that quickly, you can always make an xy table and plug in points. So is this function continuous? Yeah, there's no holes or gaps in it, so it's continuous. We're on a closed interval. Is it differentiable? So remember, a function is not differentiable at a corner, cusp, vertical tangent, or discontinuity. So right here, we've got a corner. So I'm going to say f of x is not differentiable at x equals 2. So Rolle's theorem, how do I spell that? Theorem. Okay, it's messy. So Rolle's theorem cannot be applied. F of x is not differentiable at x equals 2, so Rolle's theorem cannot be applied. The conditions aren't met. All right, let's look at number 11. We got sine curve. We had that on our mean value side. Looks something like that. So that is a continuous function. We are on a closed interval, and it's a nice smooth curve, so it's differentiable. So our 3 conditions are met. So now we have another condition that has to be met to apply Rolle's theorem, and that's this right here. F of a must equal f of b. I'm going to write that here. F of a must equal f of b. So we want to see, does ours, in this particular case, are those 2 things equal? So does f of 0 equal f of 2 pi? So if we plug in 0 here to our function, we'd get sine of 0. Is that equal to sine of 2 pi? So you think about our unit circle. Sine of 0 is right here at 1, 0, so that side's 0. Sine of 2 pi is all the way back here, so it's also 0. So check, yes, they are equal. So then if they are equal, then we can go ahead and figure out that f prime of c should also equal 0. So we're going to take our derivative, f prime of x equals cosine of x. And now, let's plug in our c, f prime of c equals cosine of c. And we know that this now, for Rolle's theorem, has to be 0. We've got 0 equals cosine of c. So think about on your unit circle, when is cosine 0? It's going to be 0 here and here. And that is when c would equal pi over 2 and 3 pi over 2. So there's actually 2 locations, and you can see those locations quite clearly in our graph because this is 0 right here and this is 2 pi. So if I made my secant line connecting those two, which is where f of a equals f of b, that has a slope of 0. Well, there's clearly 2 other points on this interval from 0 to 2 pi that would have a slope of 0. One would be here, and one would be here. And that happens to be pi over 2 right there, and then 3 pi over 2 right there. All right, let's look at number 12. So number 12, we've got a cube root function. Ooh, that's a fun little one to graph. So cube root function, a couple things here. A little side note, the cubic function, like y equals x cubed, that looks something like that. So the cubic function actually looks similar, but it goes sideways like that. But this is the cubic function minus 1, the cube root of x minus 1. So this one actually gets shifted down 1 and then does something like that. So let's check this. This is a continuous function, so check continuous. It works out. Check closed. Differentiable. That's smooth. Are there any corners, cusps? No. Vertical tangent. There is a vertical tangent. You can see it better in this graph that I drew right here than this one, but they're both, I maybe smoothed that one out, made that one a little bit flatter there. You could see it better. But there's a vertical tangent right in the center of our cubic or cube root function. But the question is, do we care about that? So let's see, if my vertical tangent's occurring here at 0, is that a problem? Yeah, 0 is included on this interval. So I'm going to say f of x is not differentiable at x equals 0. So Rolle's theorem can not be applied. However, I want to show you one other thing. Say you didn't catch that. You didn't realize that it wasn't differentiable at 0, and you just proceeded to the next step, which was, does f of a equal f of b? If you had done that, you would have had f of negative 8 equal, does it equal f of positive 8? And if you plugged that in, you would have ended up getting negative 3 equals 1, because you'd have a cube root of negative 8 is negative 2 minus 1. The cube root of positive 8 is 2 minus 1. So anyway, you would have ended up with that, which is not equal. So then you could say, okay, Rolle's theorem does not apply because f of negative 8 does not equal f of 8. So you would have figured that out even if you hadn't caught that it was differentiable. That was not differentiable. All right, let's look at number 13. Oh, we've got another rational function. This rational function has a vertical asymptote at x equals 2 because the denominator cannot equal 2. It would be undefined, so it looks something like this. You could plot some points. So you could plug in like 3 and you'll get 1. So you quickly can figure out that your function looks something. Let's see, if I plugged in 0, I'd get negative 1/2. So it's going to look something like that. So this function is not differentiable at 2 because there's a vertical tangent there, but let's confirm first that is the function continuous. The function is not continuous at 2. Oh, that's a big problem. The function is not continuous at 2. Look back up at our original statement here where it says f of x is continuous on the closed interval a to b. So it needs to be continuous on the closed interval. It only needs to be differentiable on the open interval, but we're talking about continuity right now, and so on the closed interval, 2, that's on our interval. So, done. F of x is not continuous at x equals 2, so Rolle's theorem cannot be applied. All right, number 14. The sine squared graph, well, like sine, sine squared is also a continuous curve. We can say check continuous. It's a closed interval, check closed. And like the sine curve, it's also differentiable. Check that is differentiable. In fact, if you want to see what that looks like, let me sketch that out for you real quick so you can see what the sine squared curve looks like. So we're going to make sure if you're graphing it, you're in radian mode. So y equals, we've got parentheses sine of x quantity squared. And my window is going to go from negative pi over 2 to positive pi over 2. And let's see what my y's, let's make my y's go negative 5 to 5. See what happens right there. So notice, because we're squaring it, we have no negative values under here. I'm going to just draw a little picture of what that looks like. So it's nice, smooth, ooh, something like that. Could have been centered a little bit better, but you get the idea. Hopefully, it should look something like that. All right, so all 3 conditions are met in this case. So now we need to show that does f of a equal f of b. So is f of negative pi over 2, does that equal f of positive pi over 2? So I'm going to plug in sine of negative pi over 2, and then that whole thing is quantity squared because of the squared, equals sine of positive pi over 2, and again the whole thing is quantity squared. So sine of negative pi over 2, well, let's see, negative pi over 2 on my unit circle, instead of going up to positive pi over 2, I'd go down to negative pi over 2. So down here I'm at 0, negative 1. So I'm at negative 1 squared, it's not sine, it's my y value. So does that equal sine of positive pi over 2? Well, sine of positive pi over 2 is up there at 0, 1. So that's 1 squared. Square a negative, you get positive 1 equals 1, so check. So f of a does equal f of b. So all the conditions of Rolle's theorem are met, which means now the derivative of this has to equal 0. So let's go ahead and derive it. F prime of x equals, it's the chain rule. You've got the 2 comes down in front, the inside stays the same, times the derivative of sine is cosine. Set that equal to 0, so we get 0 equals 2 sine of x, cosine of x. And if that 2 bothers you a little bit, it bothers me a little bit, I'm going to just go ahead and divide both sides by 2. So then I end up, I'm going to move this all the way down. So I end up with 0 equals sine of x times cosine of x. And then I'm going to set each piece equal to 0, sine of x equals 0, and cosine of x equals 0. Sine is 0 here and here, so when x equals 0 and pi. And cosine is 0 here and here when x is pi over 2 and 3 pi over 2. So I think, oh, do I have 4 answers? Well, if I were a larger interval, I could have 4 answers, but I only care about the value that is on the interval between negative pi over 2 and positive pi over 2. So negative pi over 2 would be down here, positive pi over 2 would be up here, so I'm looking for somewhere in there. Pi is not there. Pi over 2 and 3 pi over 2 are right there, but that's the original points that I was working with to begin with. Negative pi over 2 is the same thing as 3 pi over 2. So the only one that is between negative pi over 2 and positive pi over 2 is just that pi. No, not that pi, sorry, just that 0. Oh, and I just caught myself. I did one thing that I wish I didn't do. And all the other ones I changed them to were C's, and I forgot to do that here. So I probably would have preferred had I plugged in my C's earlier. So let's, I could go back and change those to C's here. There we go. So my final answer will be when C equals 0. And if you look at the graph, not shocking, you know, if negative pi over 2 was, let's say, right here, and positive pi over 2 is here, slope is 0, well, right there, my slope is 0 at 0. All right, and our last one, number 15, we've got an absolute value function. Absolute value this graph is going to get shifted down to, so it's going to look something like that. So is it continuous? Yes, check continuous. Is it closed? Yes, check closed. Is it differentiable? And I would say no, it's not differentiable because there's a corner, but it only has to be differentiable over the open interval a to b, which means we're not including the endpoints. So from 0 to 4 here, not including that endpoint, it is differentiable. So that's an interesting one. So it is differentiable on that open interval from 0 to 4. It has to be continuous on the closed interval, but only differentiable on the open interval. And so now we need to see, does f of a equal f of b? So does f of 0 equal f of 4? Plug in 0, we get negative 2. Plug in 4, we get positive 2. Not true. So we can write f of x is not well, probably need to say, let's rephrase that. Let's say Rolle's theorem cannot be applied on 0 to 4 since f of 0 does not equal f of 4. All right, now your final assignment is to answer this question. Describe some similarities and some differences between the mean value theorem. And I want at least 2 complete sentences. At least 2 complete sentences. All right, have a wonderful day, everybody. See you tomorrow.